Alright, let's do some physics. I will be teaching you guys about chapter 29, which deals with reflection and refraction. My objectives for this lesson are for you to understand the difference between regular reflection and diffuse reflection, for you to be able to distinguish between the different types of mirrors and how their curvature affects the resulting image, and for you to understand what refraction is and how it affects light rays in changing media. Let's start with a basic question. What is reflection? Our textbook defines reflection as the bouncing back of a particle or wave that strikes the boundary between two media. This is basically stating that a source of energy is bouncing off of a reflective surface. There are two ways that light can be reflected: a specular reflection, in which light is reflected in a single outgoing direction, or a diffuse reflection, in which light is diffused in many directions due to the imperfections in the surface. Here's my first demo showing this in action. As you could see from that demo, when the light was reflected specularly, the light rays stayed together and formed one point on the ceiling. But when the light rays hit the rough paper, they diffused and formed a green light on the ceiling. One important term that you'll need to know for this lesson is normal. The normal is the line perpendicular to the surface between two media. So let's use the normal now to predict the reflection of light. When light is reflected specularly off of a surface such as a mirror, the angle of incidence and the angle of reflection will be the same from the normal. We can see this happening in the second demo. As you could see from that demo, if you know what the angle of incidence will be, you can predict the angle of reflection. I've used a mirror for both of these demonstrations, but what is a mirror? It is not, as we see from cartoons, a portal into a strangely familiar world, but instead it is an object that reflects light and makes the object look as if it is still there. We encounter mirrors every day, and there are three main types: flat, or sometimes called plane, concave, and convex. We have all looked inside of some of these mirrors without ever realizing it. Flat mirrors are usually found in clothing stores in the dressing rooms. A concave mirror is what you use when applying makeup. And convex mirrors are located sometimes on side mirrors and on trucks and vans on the back of them, so that they have a better view of what is going on around them. Let's go a little bit more in depth with mirrors. First, flat mirrors. When you look into a flat mirror, your image is not distorted because the mirror lacks curvature. Because of this, any object that you place in front of the mirror will remain the same size regardless of the distance from the mirror. But in most situations with most mirrors, the object is not actually in the mirror. The light is being reflected off of the reflective surface and it is entering your eye, and your brain is then processing that and putting an object behind the mirror as if it is actually there. Next, let's talk about convex mirrors. In this example, light is reflecting off of the person's face, hitting the mirror, and then bouncing outwards. Our brain interprets this, follows the lines behind the mirror, and then puts a small image behind it. This is why objects in a convex mirror look smaller and seem to be rounded around the edges of the mirror. In addition to this, the greater the curvature of the mirror, the smaller the object will appear in it. Now let's move on to concave mirrors. Concave mirrors do the opposite of what convex mirrors do. They magnify the object. In this example, light is bouncing off of the person's face, hitting the mirror, and then focusing behind them. Our brain follows these light rays behind the mirror and then interprets this by putting a magnified image behind the mirror. This is why when you look into a concave mirror, your face seems to take up the whole entire mirror, when in reality, there is no real image there. Concave mirrors do the opposite of convex mirrors. As the curve gets larger, the magnification increases. The issue that comes up with mirrors is there is no real image that is created. Your mind creates the image behind the mirror, and there is actually nothing there. But that is actually not true for concave mirrors in one situation. Here's a diagram of light bouncing off of a concave mirror, meeting at a focal point, and then continuing on. Normally when you're using a concave mirror, you're up close to the mirror in the green area, and this is the image that you would see. as you begin to back away from the mirror, you will reach the focal point, and this is the image that you would then see. Once you pass the focal point, you reach an area where a real image is created. This is a real image because your brain is not creating what you see, you're actually seeing the real light being reflected. Let's move away from mirror science and have some fun with mirrors. What happens when you face two mirrors at each other? If anyone has ever seen this in person, it is called a mirror tunnel. Because we live in a real world, there is no such thing as a perfect mirror, so every time light bounces off of one mirror and hits the other, it loses a tiny bit of energy, and when this is done enough, you can actually see that light is completely lost. After showing you that, a good question to ask is, what color is a mirror? Most people will guess that a mirror is silver because of the images you see, they are portrayed with a silver color, as well as other colors such as white, black, clear, or no color at all. None of this is actually correct. A mirror is the color of whatever object you put in front of it, so if you stand in front of a mirror, it is technically you colored. There was some research done as to what colors a mirror best reflects, and it was found that it best reflects colors around the 510 nanometer range, which is actually what we perceive as green. That is why when you look at the mirror tunnel, the image gets greener and darker as you look further down. Let's move on to the second part of this chapter, which deals with refraction. Refraction, as defined by our book, is the change in direction of a wave as it crosses the boundary between two media in which the wave travels at different speeds. A simpler way to put this is that light usually slows down when it enters a different material. Let's use an analogy to figure this one out. Let's say you have a toy car that is traveling on asphalt and is going to change onto grass. As the car begins to enter onto the grass, the front right tire slows down and the left side of the car is pulled around, turning the car slightly. This is what is happening with light as it changes from one media to another. This is Snell's law, a law that is used to define the angle of refraction and the indices of refraction. Once again, the normal is used in these problems to describe the line perpendicular to the two surfaces. In these problems, the angles used are calculated from the normal, and the ends in the problem are equal to the indexes of refraction for the media. Every media has an index of refraction which is used to find the angle at which light would bend if two of these media met. The larger the index of refraction, the further the light will bend from the normal. Let's do an example of this, air meeting water. Air has a lower index than water, so when light coming from air meets the water, it will bend towards the normal because it slowed down. In this example, cooking oil is meeting air. Because cooking oil has a higher index of refraction than air, the light coming from the cooking oil will speed up when it hits the air, in turn moving away from the normal. In this example, light is moving through cooking oil into Pyrex. Because these two substances have the same index of refraction, the light will stay at the same angle because the index of refraction is the same. But what does this really mean? Let's take a look at Demo 3. So once again, what was going on in this demonstration? I had two Pyrex beakers, one inside of the other. As I began to pour the cooking oil into one, it filled the glass and then began spilling over. As it covered the other glass, it began to disappear because the index of refraction between the Pyrex glass and the old cooking oil was the same. Refraction can be found in real life when taking a look at spearfishing. The light bends when it enters the air from the water because the air has a lower index of refraction than the water. Our brains then follow this straight line from the air to an imaginary fish that is in front of the real one. If you were to throw your spear at this imaginary fish, you would actually miss the one that you're trying to hit. So a good strategy is to actually aim for the tail, because then you'll end up hitting the fish that you want to. In review, Diffuse reflection happens when light hits a rough surface and scatters. There are three different types of mirrors: plane or flat mirrors, convex, and concave mirrors. A mirror is the color of the object that you put in front of it, and refraction happens when light slows down or speeds up when changing media.